I'm going to tell you something that might shock you. I won the Nobel Prize in physics for my work on quantum electrodynamics. I've spent decades working with quantum mechanics. I've calculated things using quantum theory to incredible precision, 10 decimal places. I've taught it to thousands of students. I've written papers about it. I've given lectures about it all over the world. And I don't understand it. Nobody understands quantum mechanics. Not me, not you, not Einstein, not Bohr, not anyone who's ever lived. Now, I know what you're thinking. Wait a minute, Feynman. If you don't understand it, how did you win a Nobel Prize for it? How can you calculate with it? How can you teach it? That's a very good question, and the answer gets at something fundamental about what it means to understand something. You see, there are different kinds of understanding. There's the kind where you can use something, predict with it, calculate with it. That kind of understanding we have. Quantum mechanics works. It works incredibly well. We can use it to predict how electrons behave, how light interacts with matter, how atoms bond together. The predictions are stunningly accurate. But then there's another kind of understanding. The kind where things make sense to you, where you can picture what's happening, where your intuition tells you, yes, of course it works that way. That kind of understanding, we don't have it. Not for quantum mechanics. And here's what's really interesting. I don't think we're ever going to have it. Because quantum mechanics isn't just counterintuitive. It's not just a little weird. It describes a reality that is fundamentally incompatible with the way our brains evolved to understand the world. Let me give you an example of what I mean. You know how you understand a ball. You throw a ball, you know where it's going. You can see it, you can touch it. It's either here or it's there. It has a definite position. It has a definite speed. It follows a definite path. Your brain evolved over millions of years dealing with objects like balls, rocks, trees, animals, things that have definite positions and follow definite paths. But electrons don't work like that. Photons don't work like that. At the quantum level, particles don't have definite positions until you look at them. They don't follow definite paths. They sort of smear out. They exist in multiple places at once. They interfere with themselves. And I can tell you this, I can calculate it, I can show you the mathematics, I can show you the experiments that prove it's true. But I can't make it make sense to you. I can't make it intuitive. I can't give you a mental picture that captures what's really happening. Because what's really happening is so strange, so alien to our everyday experience, that our brains simply aren't equipped to grasp it directly. This bothered me for years. When I was first learning quantum mechanics, I kept thinking, I'm missing something. There must be some way to picture this that makes it all make sense. I'd talk to other physicists. I'd ask them, do you understand this? Does this make sense to you? And they'd say, oh yes, of course. It's quite simple, really. And I'd think, what's wrong with me? Why don't I get it? Then much later I realized they didn't understand it either. They'd just gotten used to it. They'd learned to stop asking the question. But that's not understanding. That's just familiarity. Understanding would be if you could explain it to someone in a way that makes sense, not just mathematically, not just showing them the equations, but in a way that connects to their intuition, their experience, their sense of how things should work. And for quantum mechanics, we can't do that. We can teach you the mathematics. We can show you the experiments. We can train you to calculate. But we can't make it make sense. Because it doesn't make sense. Not to human brains. Not in the way we normally think about the world. And you know what? That's one of the most profound discoveries in all of science. So what is quantum mechanics? What is this thing that nobody understands? Let me start with what it's not. It's not a theory about really small things being different from big things in some minor way. It's not just regular physics, but tinier. Quantum mechanics is a fundamental description of how nature works at the deepest level we've been able to probe. And it tells us that reality itself, the basic fabric of existence, is nothing like what we thought it was. Here's the central mystery. Particles behave like waves until you measure them. Then they behave like particles. An electron, if you're not looking at it, spreads out like a wave. It goes through multiple paths at once. It interferes with itself. It's not in one place, it's sort of everywhere at once, with different probabilities. But the moment you measure it, the moment you look to see where it is, boom, it's in one place. It has a definite position. The wave collapses. Why? How does the electron know you're looking at it? What counts as a measurement? When exactly does the collapse happen? These questions have bothered physicists for 100 years, and we still don't have good answers. Let me tell you about the most famous quantum experiment, the double-slit experiment. This experiment, more than any other, shows you just how weird quantum mechanics is. You have a source that shoots out electrons, one at a time. You have a barrier with two slits in it, and you have a screen behind the barrier that records where the electrons hit. If electrons were just little particles, like tiny bullets, what would you expect? Each electron would go through one slit or the other, and you'd see two bright spots on the screen, one behind each slit. But that's not what happens. Instead, you see an interference pattern, light and dark bands, the kind of pattern you get with waves. The electrons are somehow going through both slits at once and interfering with themselves. Okay, you say, so electrons are waves. But wait, each electron hits the screen at a single point. It makes a single dot. It doesn't spread out. When it arrives, it's a particle, not a wave. Okay, you say, so maybe the electrons are interacting with each other? Maybe the wave pattern comes from multiple electrons? But no, you can shoot the electrons one at a time with long gaps in between. Wait 5 minutes between each electron if you want. It doesn't matter. The pattern still builds up. Each individual electron somehow knows about both slits. Okay, you say, maybe the electron goes through one slit, but it's influenced by the other slit somehow. So you try to catch it in the act. You put detectors at the slits to see which one each electron goes through. And here's where it gets really weird. The moment you do that, the moment you try to see which slit the electron goes through, the interference pattern disappears. Now you get two bright spots. The electrons start behaving like particles. Just by looking, by measuring which slit they go through, you change what happens. The act of observation changes the outcome. Now, this isn't just a problem with our measurement equipment. This isn't we're disturbing the system. This is fundamental. This is telling us something deep about how reality works. The electron, when you're not looking, actually goes through both slits. It exists in what we call a superposition, a combination of both possibilities. It's not that we don't know which slit it went through. It's not that it went through one slit and we just haven't figured out which one yet. No, it actually, truly, goes through both slits at the same time. And the moment you measure it, the moment you look somehow, in a way we don't fully understand, the superposition collapses. The electron chooses one slit. It becomes definite. This is what quantum mechanics tells us. And it's been verified in countless experiments. It's not speculation. It's not just a theory. It's what nature actually does. But it doesn't make sense. Not in any normal way. Einstein hated this. He couldn't accept it. He kept coming up with thought experiments, trying to show there must be something wrong with quantum mechanics, some hidden variable we're missing, some deeper explanation that would make it all make sense. He'd say, God doesn't play dice with the universe. And Bohr would reply, Einstein, stop telling God what to do. But Einstein was right to be bothered. Because quantum mechanics is genuinely bizarre. It violates our deepest intuitions about how reality should work. Things should have definite properties, whether we look at them or not. A tree falling in a forest makes a sound, even if nobody's there to hear it. The moon exists when we're not looking at it. But at the quantum level, things don't have definite properties until you measure them. Position, momentum, energy, these aren't things particles have. These are things particles acquire when you measure them. Before measurement, there's just the wave function, a mathematical description of probabilities. After measurement, there's a definite outcome. What happens in between? How does it work? Why does measurement matter? We don't know. Quantum mechanics didn't start out this weird. It started with some puzzles, some things that classical physics couldn't explain. In the early 1900s, physicists were feeling pretty good about themselves. Newton's laws explained motion. Maxwell's equations explained electricity and magnetism. We understood heat, light, energy. We thought we pretty much had it all figured out. Then some cracks started appearing. Blackbody radiation. When you heat up an object, it glows. The color of the glow depends on the temperature. Classical physics predicted that as you went to shorter and shorter wavelengths, ultraviolet and beyond, the intensity should increase without limit. The ultraviolet catastrophe. But that's not what happened in experiments. The intensity peaked at a certain wavelength and then dropped off. In 1900, Max Planck figured out how to fix the equations. He proposed that energy comes in discrete chunks, quanta. Light isn't continuous. It comes in packets. He thought this was just a mathematical trick, something to make the equations work. He didn't think it was real, but it was real. Then Einstein showed that light really does come in packets, photons. The photoelectric effect only made sense if light was made of particles with definite energies. Then Niels Bohr applied quantum ideas to atoms. Why don't electrons spiral into the nucleus? Because they're only allowed certain specific orbits, certain specific energy levels. They can't be in between. Why? Nobody knew. That's just how it was. Then Louis de Broglie suggested that maybe particles like electrons also have wave properties. If light can be both wave and particle, maybe matter can too. And experiments confirmed it. Electrons make interference patterns. Particles have wavelengths. By the mid-1920 seconds, physics was a mess. Particles acted like waves. Waves acted like particles. Nothing made sense anymore. Then, in 1925 and 1926, the whole thing came together. Heisenberg developed matrix mechanics. Schrödinger developed wave mechanics. Both gave the same results, and both worked incredibly well at predicting experimental outcomes. They called it quantum mechanics, and it revolutionized physics, but nobody understood what it meant. Heisenberg said, you can't know both position and momentum precisely at the same time. There's a fundamental limit, the uncertainty principle. And this isn't because our measurements are clumsy. It's because particles don't have definite position and momentum at the same time. Schrödinger wrote down an equation, the Schrödinger equation, that describes how the wave function evolves. It's a beautiful equation. It works perfectly. But what is the wave function? What does it represent? Schrödinger thought it represented something real, some kind of actual wave in space. But Max Born showed that it represents probability. The wave function tells you the probability of finding the particle at different locations if you measure it. But what's waving then? Probability? What does that even mean? Schrödinger hated this interpretation. He wished he'd never invented the equation. Then came the famous Bohr-Einstein debates. Einstein kept coming up with thought experiments to show quantum mechanics must be incomplete. Bohr kept showing why Einstein was wrong. At the 1927 Solvay conference, all the giants of physics gathered to argue about quantum mechanics. Einstein, Bohr, Heisenberg, Schrödinger, Planck, Born, de Broglie, Dirac. They couldn't agree. They argued for weeks. And by the end, they still couldn't agree on what quantum mechanics meant. The Copenhagen interpretation, Bohr's view, became the dominant interpretation. It says, the wave function is complete. It tells you everything there is to know. Particles don't have definite properties before measurement. Measurement creates reality. But many physicists never accepted this. Einstein certainly didn't. Schrödinger didn't. De Broglie didn't. They felt there must be something deeper, some hidden variables, some underlying reality that quantum mechanics was just scratching the surface of. And the debate continues to this day. There are different interpretations of quantum mechanics. The Copenhagen interpretation, the many worlds interpretation, the pilot wave interpretation, the transactional interpretation. They all give the same predictions for experiments, but they tell very different stories about what's really happening. Which one is right? We don't know. We can't tell because they all predict the same experimental results. This is what I mean when I say nobody understands quantum mechanics. We have a mathematical formalism that works perfectly. We can calculate anything you want, but we don't know what it means. We don't know what's really happening. When I was at Cornell, I'd teach quantum mechanics to graduate students, smart students, and they'd ask me, Professor Feynman, what's really happening when the wave function collapses? And I'd say, I don't know. Nobody knows. Don't waste your time worrying about it. Just learn how to calculate. Was that a good answer? Maybe not. But it was an honest answer. The moment I realized that not understanding was okay, that it was actually liberating, came during my work on quantum electrodynamics. This was in the late 1942. I was at Cornell. The war was over. I'd come back from Los Alamos, and I was trying to figure out how to deal with infinities in quantum field theory. See, when you tried to calculate things in quantum electrodynamics, the quantum theory of how light and matter interact, you kept getting infinite answers, which obviously didn't make sense. Other people were trying to sweep the infinities under the rug, or they'd say, we need to find the true theory that doesn't have infinities. But I took a different approach. I said, what if I just stop trying to picture what's really happening? What if I just focus on what we can measure? I developed a new way of calculating Feynman diagrams, little pictures that represent different ways particles can interact. You draw all the possible diagrams, calculate the amplitude for each one, add them up, and you get your answer. But here's the key. The diagrams aren't pictures of what's really happening. They're just calculation tools, just ways to organize your math. An electron emits a photon, which is absorbed by another electron. That's one diagram. But you can also have the electron emit two photons, or emit a photon and reabsorb it, or emit a virtual electron-positron pair. Are these real processes? Are they really happening? I don't know. I don't care. The diagrams work. They give you the right answers. That's all that matters. This was a revelation for me. I realized I don't need to understand what's really happening at the quantum level. I don't need a picture in my head that makes sense. I just need a reliable way to calculate what we'll observe in experiments. And quantum mechanics gives us that. It gives us a precise mathematical way to predict outcomes. It works to incredible accuracy. The magnetic moment of the electron, we can calculate it to 10 decimal places, and it matches the experimental measurement to 10 decimal places. That's like predicting the distance from New York to Los Angeles to within the width of a human hair. So quantum mechanics works spectacularly well, better than any theory in the history of science. Does it make sense? No. Can we picture what's happening? No. Do we understand it? No. But we can use it. We can predict with it. We can build technology with it. And maybe that's enough. Maybe that has to be enough. Here's what I realized. The problem isn't quantum mechanics. The problem is our expectation of what understanding should feel like. We expect understanding to mean having a mental picture, being able to visualize what's happening, having it make intuitive sense. But that expectation comes from our experience with the everyday world. The world of baseballs and cars and falling apples. The world our brains evolved to navigate. At the quantum level, things just don't work like that. They're not supposed to make sense to our monkey brains. They're not supposed to be intuitive. Our intuitions are evolved. They were selected for because they helped our ancestors survive on the African savanna. They're very good at dealing with medium-sized objects moving at medium speeds, but they're terrible at dealing with things moving near the speed of light, and they're terrible at dealing with things at the quantum scale. So, of course, quantum mechanics doesn't make sense to us. It's describing a reality that's completely outside our evolutionary experience. The miracle isn't that quantum mechanics is hard to understand. The miracle is that we can understand it mathematically. That we can develop a formalism even though it doesn't make intuitive sense that lets us predict what will happen. That's actually amazing. That's a triumph of human reasoning. We managed to figure out how nature works at scales we can never directly experience, using tools, mathematics, that go beyond our intuitions. We can't visualize it, we can't picture it, but we can calculate it, we can work with it, we can make predictions, and those predictions are right. That's understanding, even if it doesn't feel like the kind of understanding we're used to. This realization freed me. I stopped worrying about whether I really understood quantum mechanics. I stopped trying to make it make sense. I focused on learning how to use it, how to calculate with it, how to make predictions. And it worked. I made progress. I contributed something useful. I won a Nobel Prize, all without understanding quantum mechanics in any intuitive sense. Okay, so let me try to give you a sense of what quantum mechanics actually says. Not an intuitive picture, because there isn't one, but at least the core ideas. First principle, the wave function. Every particle, every electron, every photon, every atom has a wave function. We write it as psi, the Greek letter psi. The wave function is a mathematical object. It's a function that assigns a complex number to every point in space. What does it mean? It encodes all the information about the particle's state, where it's likely to be, what momentum it's likely to have, what energy it has. But here's the key. The wave function doesn't tell you where the particle is. It tells you where it might be. It gives you probabilities. If you square the magnitude of the wave function at some location, you get the probability of finding the particle at that location if you measure it. Before you measure, the particle isn't at any particular location. It's described by the wave function, which is spread out over space. When you measure, you get one particular outcome, and the wave function collapses to reflect that outcome. This is weird. Before measurement, the particle is in a superposition. It's sort of in many places at once. After measurement, it's in one place. What causes the collapse? When exactly does it happen? These are deep questions that physicists still argue about. Second principle, the uncertainty principle. Heisenberg showed that there are pairs of properties like position and momentum that you can't know precisely at the same time. The more precisely you know the particle's position, the less precisely you can know its momentum, and vice versa. This isn't because our measurements are clumsy. It's not a technical limitation. It's fundamental. The particle doesn't have both precise position and precise momentum at the same time. Why? Because in quantum mechanics, these properties are represented by operators that don't commute. The math literally doesn't allow you to have precise values for both simultaneously. Again, this is weird. We're used to objects having definite positions and definite velocities, but at the quantum level, they don't. Third principle, superposition. A particle can be in a superposition of states. It can be in multiple places at once. It can have multiple energies at once. It can be spin up and spin down at the same time. This isn't just we don't know which state it's in. It's genuinely in multiple states simultaneously. When you measure, you get one outcome. But before measurement, it's actually in all the states at once, with different probability amplitudes. This is what allows quantum interference. The different parts of the superposition can add up or cancel out, creating interference patterns. Fourth principle, entanglement. This one really bothered Einstein. He called it spooky action at a distance. If two particles interact, they can become entangled. Their wave functions become linked. You can't describe one particle independently of the other anymore. Now, here's where it gets weird. You can separate the particles, take them to opposite ends of the universe if you want. They're still entangled. If you measure one particle and get a particular outcome, the other particle instantly knows about it. Its wave function changes instantly to be correlated with your measurement. Einstein thought this proved quantum mechanics must be wrong. He thought there must be some hidden information that both particles carry with them. But experiments have shown Einstein was wrong. The correlation really is instantaneous, and there are no hidden variables. This doesn't violate relativity, because you can't use entanglement to send information faster than light, but it's still deeply weird. Now, let me tell you about my approach to quantum mechanics, the path integral formulation. In normal quantum mechanics, you think of a particle having a wave function that evolves according to the Schrödinger equation. In my formulation, you think of the particle as taking all possible paths from start to finish, all of them, simultaneously. Want to know how an electron gets from point A to point B? It takes every possible path. Straight line, curved paths, zigzags, loops, paths that go to Mars and back, every conceivable path. Each path contributes an amplitude. You add up all the amplitudes from all the paths. The result tells you the probability of finding the particle at B if it started at A. Is the electron really taking all these paths? I don't know. That's just how you calculate. But here's what's interesting. For most paths, the amplitudes cancel out. The path to Mars and back interferes destructively with similar paths. All the crazy paths largely cancel each other. What's left? Mostly the paths close to the classical path, the straight line, or whatever path classical physics would predict. So classical physics emerges as an approximation. It's what you get when you average over all the quantum paths. But the quantum paths are always there, and for very small particles or very short distances or very low energies, they matter. The path to Mars and back doesn't quite cancel out completely. It contributes a tiny bit, and sometimes that tiny bit makes a difference. This is how quantum effects work. It's not that particles sometimes follow weird paths. It's that they always follow all paths, but most of the weird ones cancel out under normal conditions. Does this help you understand quantum mechanics? Probably not. Does it give you a picture of what's really happening? No. But it gives you a way to calculate, and the calculations work. Let me try one more example, Schrödinger's cat. You've probably heard of this. It's a thought experiment Schrödinger came up with to show how weird quantum mechanics is. You put a cat in a box with a vial of poison. The vial is connected to a radioactive atom. If the atom decays, it triggers a mechanism that breaks the vial and kills the cat. Radioactive decay is a quantum process. The atom is in a superposition of decayed and not decayed. So, according to quantum mechanics, until you open the box and look, the cat is in a superposition of alive and dead. It's both alive and dead at the same time. This sounds absurd, and Schrödinger meant it to sound absurd. He was trying to show that quantum mechanics can't be right because it leads to ridiculous conclusions when you apply it to everyday objects. But the math doesn't care about our sense of absurdity. The math says the cat is in superposition. So what's going on? Why don't we see cats that are both alive and dead? One answer: the cat is a measurement device. It observes whether the atom decayed, so the wave function collapses inside the box before you open it. Another answer: superpositions of large objects are incredibly fragile. The slightest interaction with the environment, a single air molecule bouncing off the cat, destroys the superposition. This is called decoherence. A third answer: the universe splits into two branches. In one branch, the cat is alive. In another branch, the cat is dead. Both branches are real. You just only experience one of them. This is the many worlds interpretation. Which answer is right? We don't know. They all give the same predictions for what you'll see when you open the box. This is what I mean when I say we don't understand quantum mechanics. We can calculate what will happen, but we don't know what's really happening. So why does this matter? Why am I spending all this time telling you about something I don't understand? Because I think there's something profoundly important about the fact that quantum mechanics works even though we don't understand it. It tells us something about the nature of understanding itself, about what it means to know something, about the relationship between mathematics and reality. For thousands of years, humans have tried to understand the world. We've built models, created theories, told stories about how things work. And for most of that time, understanding meant having a story that made sense, that you could picture, that connected to your everyday experience. The earth is flat because it looks flat. Heavy objects fall faster because they're heavier, that's obvious. The sun goes around the earth because you can see it moving across the sky. These explanations feel right. They make intuitive sense. They're wrong, but they feel right. Then science came along and said, your intuitions don't matter. What matters is what you can test, what you can measure, what you can verify. And slowly, we learned that reality doesn't match our intuitions. The earth is round. Heavy objects and light objects fall at the same speed. The earth goes around the sun. These truths don't feel right. They're not intuitive, but they're true. Quantum mechanics is the culmination of this process. It's the ultimate departure from intuition. At the quantum level, particles don't have definite properties until you measure them. They exist in multiple states at once. They're connected across vast distances. They take all paths simultaneously. None of this makes sense. None of it fits with how we think reality should work. But it's true. We've tested it again and again and again. It's how nature actually works, and we can work with it. We've built quantum mechanics into technology, transistors, lasers, computer chips, MRI machines, all based on quantum mechanics. We're using something we don't understand to build things that work, and I think that's beautiful. I think that's profound. It shows that human reason is more powerful than human intuition, that mathematics can take us beyond the limits of our imagination, that we can understand things without being able to picture them. This matters for how we approach knowledge in general. There are always going to be things that don't make intuitive sense, things that violate our expectations, things that seem impossible or absurd. The question is, do we reject them because they don't make sense, or do we accept them because the evidence demands it? Quantum mechanics teaches us to trust evidence over intuition, to trust mathematics over mental pictures, to trust what we can measure over what we can imagine. This is hard. It goes against our nature. We want things to make sense. We want to be able to picture them. But sometimes, reality is stranger than our brains can handle. And that's okay. We can still learn about it. We can still work with it. We can still make predictions. We just have to be humble enough to admit we don't fully understand it. And you know what? That's exciting. That means there's still mystery in the universe, still things to discover, still depths we haven't plumbed. If we understood everything, if everything made intuitive sense, what would be left to discover? Now, I need to address some common misunderstandings about what I'm saying. When I say nobody understands quantum mechanics, people sometimes think I mean quantum mechanics might be wrong, or we're just guessing, or it's all uncertain and unreliable. That's not what I'm saying at all. Quantum mechanics is not wrong. It's been tested more thoroughly than any theory in history. Every prediction it makes has been verified. It's the most successful scientific theory ever developed. When I say we don't understand it, I don't mean we don't know if it's true. We know it's true. What we don't know is why it's true, what it means, what's really happening at a deep level. We have the how, we don't have the why. Another misconception: people think quantum mechanics means anything is possible, or reality is whatever you want it to be, or consciousness creates reality. No. Just no. Quantum mechanics is extremely precise. It makes specific predictions, not vague predictions, precise numerical predictions, and those predictions are either right or wrong. The universe doesn't care what you think. It doesn't matter if you believe in quantum mechanics or not. It works whether you understand it or not, whether you like it or not. The measurement problem, the question of how and why wave functions collapse, that's a real mystery. But it's not a mystery that gives you magical powers. It's a technical question about the boundary between quantum and classical behavior. Some people take quantum mechanics and use it to justify all sorts of mystical ideas. Quantum healing, quantum consciousness, the secret, law of attraction. These are nonsense. They have nothing to do with real quantum mechanics. Real quantum mechanics is about electrons and photons and atoms. It's about very small things in carefully controlled conditions. It's not about thoughts creating reality or visualization making things happen. Don't confuse not understanding something with it being magical or mystical. We don't understand quantum mechanics, but we understand it precisely enough to make predictions to 10 decimal places. That's not magic, that's science. Another thing, when I say particles don't have definite properties before measurement, that doesn't mean everything is relative, or there's no objective reality. There is an objective reality. The wave function is objective. The results of measurements are objective. Different observers will see the same results. What's weird is that the wave function doesn't describe definite properties. It describes probabilities, but those probabilities are objective. They're the same for everyone. This isn't philosophy. This isn't interpretation. This is what the math says and what the experiments show. One more thing, different interpretations of quantum mechanics. I mentioned earlier that there are different ways to interpret quantum mechanics. The Copenhagen interpretation, many worlds, pilot wave theory, and others. These interpretations tell different stories about what's really happening, but they all give the same experimental predictions. Some people get very invested in one interpretation or another. They'll argue passionately that their interpretation is right and the others are wrong. But here's the thing. If they all make the same predictions, how can you tell which one is right? You can't. Not with any experiment we can currently do. So, which interpretation should you believe? I don't know. I don't think it matters much. Pick whichever one helps you think about the problems you're working on. I tend to use the path integral formulation because it's useful for the calculations I do, but that doesn't mean I think it's true in some deep sense. It's a tool, a way of organizing your thinking, a way of doing calculations. Does it reflect reality? I don't know. Maybe, maybe not. What I know is it works. So what can we learn from all this? What's the bigger lesson? I think the biggest lesson is this. It's okay not to understand something as long as you're honest about it. In science, in life, in everything, there are going to be things you don't fully understand. Things that don't make complete sense to you. Things that seem paradoxical or mysterious. The wrong response is to pretend you understand when you don't, to make up stories that sound good but aren't true, to be overconfident in explanations that don't really explain. The right response is to admit, I don't know, nobody knows. Here's what we do know, and here's where the mystery begins. This is intellectual honesty. This is integrity. I've spent my whole career working with quantum mechanics. I've probably thought about it more than most people, and I still don't understand it, and I'm okay saying that, because admitting you don't understand something is the first step to learning more about it, to pushing deeper, to making progress. If you pretend you understand when you don't, you stop asking questions, you stop looking for better explanations, you get stuck. But if you admit you don't understand, you stay curious, you keep exploring, you keep learning. There's something liberating about saying, I don't know. It takes the pressure off. It allows you to be curious rather than defensive. Another lesson, understanding isn't binary. It's not you understand it or you don't understand it. There are levels of understanding. There are different kinds of understanding. I understand quantum mechanics well enough to calculate with it, to make predictions, to solve problems, to teach others how to use it, but I don't understand it well enough to make it intuitively obvious, to give you a picture that captures what's really happening. Both of these are forms of understanding. Neither is complete. Both are valuable. This is true for everything, not just physics. You can understand how to drive a car without understanding how the engine works. You can understand how to use a computer without understanding how the processor works. You can understand how to speak a language without understanding the neuroscience of language. Different levels of understanding are appropriate for different purposes. The key is to know what level you're at, to be honest with yourself about what you understand and what you don't. One more lesson. Sometimes the universe is genuinely weird, and that's wonderful. We live in a universe that's stranger than we ever imagined. At the deepest level we can probe, reality behaves in ways that defy our intuition, that violate our expectations, that seem impossible. And yet, it's real. We can interact with it. We can use it. We can build technology with it. There's something humbling about this. It reminds us that the universe doesn't owe us an intuitive explanation. It doesn't have to make sense to our monkey brains. But there's also something exciting about it. It means reality is richer, deeper, stranger than we thought. It means there's still mystery, still things to discover. If everything made perfect sense, if we understood everything completely, how boring would that be? The fact that quantum mechanics is weird, that we don't fully understand it, even after 100 years, that keeps me interested, that keeps me working, that keeps me curious. I want to end with this thought. People often ask me, Professor Feynman, does it bother you that you don't understand quantum mechanics? And my answer is no, not at all. What would bother me is if I thought I understood it when I didn't, if I fooled myself into thinking I had it all figured out. But knowing that I don't understand it, that there's still mystery, that there are still questions to answer, that's exciting. That's what makes science fun. I've been working with quantum mechanics for decades, and I'm still learning, still discovering new things, still finding new ways to think about it. If I'd figured it all out 30 years ago, what would I have done since then? The incompleteness of our understanding isn't a bug, it's a feature. It's what keeps science alive, what keeps us asking questions, what keeps us pushing forward. So if you're learning about quantum mechanics or anything else in science, and you're feeling frustrated because it doesn't make sense, that's normal. That's how it's supposed to feel. The ones who tell you it's simple, they're either lying or they don't understand it either. The honest answer is, it's weird. It's counterintuitive. It's hard to wrap your head around. But you can learn to work with it. You can learn to calculate with it. You can learn to make predictions. And maybe, someday, someone will figure out a deeper explanation, a better way to think about it, something that makes it all click. Maybe that person will be you. But even if not, even if quantum mechanics remains mysterious for another 100 years, that's okay. Because we can still do amazing things with it. We can still explore nature. We can still build technology. We can still make discoveries. We don't need complete understanding to make progress. We just need honesty, curiosity, willingness to work with mystery. So embrace the weirdness, embrace the mystery, Embrace the fact that the universe is stranger than you imagined. And remember, nobody understands quantum mechanics. Not me, not you, not anyone. And that's perfectly okay. In fact, it's wonderful, because it means there's still more to discover, still more to learn, still more to figure out. The journey isn't over, the story isn't finished, and that's the most exciting thing of all.